Hi everyone, if you're here yet. Let me see. No, 0 watching. Oh, come on, what just happened? Okay. I'm here to answer questions and eat my dinner. Feel free to ask away. Sorry if you guys see me munching, but I'm hungry. This is how I go round the benzene bush, benzene bush, benzene bush. Now that's a fun molecule. Are you just going to sit there and be quiet? Okay. I'll just sit here and wait. I'm having some technical difficulties with my computer. For some reason it keeps minimizing my screen when I'm not wanting it to. So if that messes things up, I'm sorry, I'll fix it each time. Bicyclic's larger than a cyclopentane. I could go up to a cyclohexane. I wouldn't give anything bigger than that. Keely, why are you here? You just had an exam. No, sweetie, this isn't your class. This is organic too. They're going to have an exam tomorrow. Yeah, my students often say that when they see me around lunch and dinner time. Bye, Keely. Oh, and class yesterday didn't count because I had to take my medicine. And if I don't take medicine with my antibiotics, they make me sick. If I don't take medicine with my antibiotics, they make me sick. If I don't eat with my antibiotics, they make me sick. So you guys will get to see me eating for a while because I don't know where I put them. I've got a ton of them left. I should just stop taking them, right? I'm feeling better. Isn't that how it works? Yes, Aaron. Benzene nomenclature. Actually, a Diels alder of a single ring with something that's not a ring will also form a bicyclic. If you had 2 rings, it would be a tricyclic, I think. Alrighty. Well, let me erase this beast of a molecule. Okay. I could ask you to do what we did in class. I mean, but that's it. There's not really anything past what we did in class as far as the resonance stability goes. Push your arrows. If you push your arrows, it'll all make sense. All right. Somebody name that for me. I feel like that's kind of tiny. Let me make it a little bit bigger. That would be orthoethylmethylbenzene. What's the IUPAC name, Crystal? That's the old way. You got it. And if anybody's wondering why it's 1-ethyl, 2-methyl, and not 1-methyl, 2-ethyl, if they're equivalent in, what am I trying to say? In reactivity, like if their priority's the same, then you go alphabetically. So very nice. Now that's what's neat about the orthometapara, is that it doesn't even take that into account. It's just giving you the general direction that they are. So that's pretty nice. Let's see. Hey Kayla, I could ask for both. I told you guys to learn both because I need you to know what the orthometapara is. But if I ask you, I mean, I could use both names and expect you to know what they are. If you are naming something and I don't specify, you can do it whichever way you want. So let's see. Kayla, let me give you another one. Or Crystal, or whoever wants to do their nomenclature. Rememorize that one. What's it called? I won't count off for spelling on that one. Also, if you notice behind me, thank you, Crystal. Thank you, Kayla. I'm actually in my actual office for these online office hours instead of being from home because I completely forgot my computer on campus, so I had to drive back here because I care about you, and I told you I would be here. Okay. Let me... Ooh. Hold on. If you make me laugh, I still cough really bad. Okay. Let's do... one there. Let's do one there. All right. What is it? was one of the memorized ones too. Imidazole, that's right, Kayla. Okay, Crystal's asking, so would you ask which position would be better for resonance, or would you ask us to draw every single resonance structure? If you... No, that's not pyrimidine. Pyrimidine's the one that looks like that. That's pyrimidine. So... Sorry, I hope that's not too loud. Would you ask which position would be better for resonance, or would you ask us to draw every single resonance structure? My notes are 5 pages, so I feel like it's a lot. Crystal, that's because you write 4-inch letters. Everyone else has like a page and a half. Anyway, I could ask any. So, you know, it's important to realize that there are resonance structures, right, that are going to contribute to stability. So if you have, let me see, something like that, with, let's see, let's put those there, and maybe, ooh, let's get it really exotic here. I'll put an amine. Okay. So that amine has electrons on it, yes? I want to wait till you say yes. I forgot there's like a 10-second lag. I'll assume that you're saying yes. So this amine would be an electron donating group then. So it's going to be, thank you, Crystal. It just came through. Orthopara. Alexandra's here. Hi, Alexandra. It's going to be an orthopara director, and so you would be able to get both molecules. So if you're going to add ortho, you would add into this position. Let's see, can I highlight that in any way? I don't know if I can. This one here. Ah! No, that's not what I wanted. Let me try this. Can I do that? No, I cannot. Okay, anyway, so if you're adding to the ortho position, it would be, you know, on either of the ortho positions next to the nitrogen, or you could add it to the para position. So let's say that we're looking at adding, let's do like a nitration reaction. So we're going to be adding ortho and para. So for the ortho position, it would be, oh, hey, look, now it's red. We would be adding to that CH group. Somebody let me know if that's showing up as a bright CH that's red to you when I put my cursor on it. And so you would have your first, okay, awesome. You would have your first reagent. Who's Livy O? Oh, that's Olivia. Hi, Olivia. Okay. So I need to go through and delete. And then draw a new bond. Like that. So if I added my nitro group to there, which I will do, okay, and then, oh, come on. Kim Sketch is usually our friend, but not always. All right. So then we have the positive charge, right? So as long as you know where it's going and which bond it's going on, you should be able to figure out which one has a positive charge on it. And if you can do that, then you can start pushing the electrons, right? And it's much easier to do on paper, obviously, because you can just draw away. But the amine is going to be able to contribute electrons to that, so you'd be able to draw a resonance structure with that. Remember that resonance structures should have conservation of charge, right? So if one of them is overwhelmingly charged and the other one's not, then you didn't do it right. So if you have that molecule, you'll notice that the nitrogen stopped having a charge on it, but that's because the computer program, automatically put on a, it took off the hydrogen when I added something onto it. So that would be one resonance structure, right? Well, you could take the carbon here, I'm sorry, the double bond right there. I don't know if you guys can see that highlighted. Let me look real quick. Yeah, okay. So you could take that highlighted carbon bond and then move that, right? So if you do that, right, you're essentially just moving things around the ring. But when you move certain bonds, they're going to make it so that other bonds have to move, right? So if I have my, if I've moved my carbon bond between here and here, the nitrogen carbon bond would have to break. There's no way for that carbon to have 5 bonds on it, right? So I have to go through and just go through and add all my bonds still. As I said, this is a lot easier to do in your notes, but all you're doing then is saying, okay, where is the hydrogen going to be? Where's my positive charge going to be? So if you're having trouble doing that, Crystal is kind of who I'm answering here. If you are having trouble doing that, what I recommend is you draw all the hydrogens on your molecules. So like go through here at the very beginning. Well, that's funny, some of them are red now. I jacked that up. Come on. If you put all the hydrogens on there, and I know it seems kind of elementary at this point probably to say, yes, I'm going to put all my hydrogens on like I did in Gen Chem, but it can really help you see where you're missing a carbon with 4 bonds on it, right? So anywhere that you're going to be missing a bond, it's not suddenly that it has an extra hydrogen on it, it's just that, you know, that's where your carbocation has moved. And all those resonance structures are essentially moving that carbocation around the ring, with addition to the resonance structure that moves those electrons, or moves that charge basically onto the nitrogen by moving those electrons into the ring to stabilize the ring. I don't know if that answers your question. I hope that answers your question. So yeah, I could ask you to draw any of the resonance structures here. I could ask you to draw, I could ask you, as far as stability of resonance structures goes, we looked at the ones for the meta edition that had partial positive charges next to full positive charges, and we said those were kind of icky and those aren't super favored, so it wasn't a really good resonance structure. So I could ask you if those are bad resonance structures in comparison, and you would say yes. But that's just a simple fact of knowledge, right? Positive charge and partial positive charge next to each other are going to push each other away. So if you can remember that, though, you should be okay with that. I have faith in you. All of the faith. The middle structure with the bond and the nitrogen, no, not that one. I'm talking about with the meta directors. If we had something, all those resonance structures I just drew were fine. But if you have something that is an electron, let me see, let's put something here like this. One of those meta directors, so anything that has like the carbonyl or the nitro group. So if I have something like this, I would end up with a resonance structure, too far. Shoot. Oh, for the love of goodness. I'm like desperately trying to move my screen in a way that I don't know why my mouse isn't wanting to work on this. There we go. Okay. So if I was adding something to this, this is a meta director, right? So I would add something to the meta position. So I'm just going to show that. I'm not drawing the mechanisms with these because those do take a while, and I think you guys, sorry, every time I mess up, I'm like, All right. Okay. So between these molecules here, ortho, meta, I'll just put it at the one on the top. So let's act like we were adding on some random group. We'll call it call it R. Oh, come on now. I don't know why my computer keeps minimizing my screen when I don't want it to. Okay, so if I'm looking at this molecule here, I have to remember that there is a hydrogen there, and a hydrogen there, and a hydrogen there, and there. There's not one here because it's already got something else connected to it, and there's one there. So remember that benzene always has one hydrogen on every single carbon unless there's already some substituent on it, or if you're in the process of breaking the aromatic ring to put on a new substituent. So that means that my positive charge would have to go right here, because that would be the carbon that doesn't have 4 bonds on it, right? Formal charge we did many, many, many moons ago. Excuse me. And so if I was looking at this, I could have a resonance structure that is going to, oh, I put it in the wrong spot. Did I put it in the wrong spot? Yes, there will be Diels-Alder on the exam. That's a possibility for sure. I'm not telling you exactly what's on the exam. But I didn't. I'm trying to figure out what I did here. It doesn't look right to me. Let me stare at this for a second. And yes, we can go over a Diels-Alder. Grab a model kit if you don't have one, because I'll bring mine out. So, either way, what we try and avoid, Alexandra, and I'm just, for whatever reason, having issues right now, but what we try and avoid is molecules that have something like, wait a second. That, where you would have a positive charge, let me move that, a positive charge here on the carbon, and then a partial positive charge on the carbon next to it, or the full positive charge if you're talking about a nitro group. The nitrogen would have a full positive charge there. We try and avoid resonance structures like that. Those aren't as stable. Okay, so let me get... But that is definitely in your notes, and for some reason I'm just on the struggle bus right now. Oh, I didn't see you guys today. Let me tell you a story while I'm putting the molecule together. My dog, Red, the monster, yesterday, while I was at work, decided that it would be best if he got on the kitchen counter, because he's enormous, so he can. Why does this keep minimizing? He decided to get on the kitchen counter, like he does, because he's a monster. And he's decided to eat an entire loaf of 100% whole wheat bread. I shouldn't say a whole loaf. Brandon might have had 2 sandwiches out of it. So, yeah. He kept me up all night because he kept having to run outside to go to the bathroom. Dog's a monster. All right, so looking at a Diels-Alder type structure, which is what I'm making right now. And remember, you can use your model kits. I just didn't understand why there was a double bond to the nitrogen that makes it not aromatic. Alexandra, what are you talking about? Are you talking about this one up here? It's not that it's not aromatic. Because that's talking about the ring. That's not talking about the ring. Okay. Anyway, let me go ahead and make a dienophile, right? My diene, or my alkene. And then I'm just putting like a red group on there so we can kind of differentiate it. And then I need to make the diene itself. Now, I don't know if you guys have noticed this. Hopefully you've done enough problems that you are aware of the fact that the times that you get a bicyclic is when you already have a cyclic, right? You don't get a bicyclic unless you already have a ring somewhere. So what I'm going to do is just put together some sort of ring here. Kind of doesn't matter what, but it definitely does help if you use a model kit if you're having a hard time visualizing it. I should make my own model kits and sell them. I love these things. That'd be creepy though, wouldn't it? If I was like, hi, I'm your professor and I'm making you buy the Megan Man patented model kit. I guess other professors do that, but I try and make school as cheap and affordable as possible for you. Okay, Kayla, try doing it with model kit. So this is what I have. Okay, let me quick. I'm trying to make sure that everything I have is in the like frame of if you guys are having trouble seeing this, tell me to scoot my molecules down. So I think the easiest way to do it is to actually physically think about these molecules and then to number them. Okay, so for me, I can see things a lot better and I can come up with much better stuff if I number things. All right. So if I have these two molecules here, so this would be cyclohexadiene 1,3-diene, cyclohexa 1,3-diene, and this would be some sort of substituted propene. All right. So if I take these and I think, okay, what does a Diels-Alder reaction do? I know that the thing that's the dienophile is going to attack my exterior carbon on the diene, either one. In this case, the molecule's symmetric. If it wasn't symmetric, you could get a mixture of products, but I'm not that evil. So you can have it attack here or here. It's not going to matter. That's going to force the double bond here, and then this one is going to connect to the other side where you would leave the carbocation. Okay, so as soon as this bond breaks, you're forming a carbocation at 1 or 2. Remember, this is like a hinge opening. So we make the hinge open and it approaches in a way that you get the the endo product, right? But otherwise you just kind of need to know where things are going to bind. Okay, so I'm going to come over here to my screen and delete all that. Okay, so I'm putting up cyclohexadiene. There you go. And I'm going to put in the molecule that I made. We'll act like that is a we'll put it in as an oxygen, just for the sake of conversation, okay? So what I know is that, I need to change my stereochemistry. So what I know is that the dienophile and the diene are what react with each other, right? So if I look at the dienophile as attacking the diene, that's going to facilitate that pericyclic reaction we've been talking about, right? So what I like to do is go here And I mean, I'm serious, like physically number it. So we'll call that carbon 1. We'll call that carbon 2. I will call, let's see, that 3. And 4. 5. 6, 7, and 8. Now, if you notice, I didn't number that last methyl group on the propane, or the propanol. And I did that because we don't really need it to make our ring. Like, the carbons that you have to keep track of are the ones in the ring, right? So I have carbons 1 and 2, like this, and 3, 4, 5, 6, 7, and 8 over here, all right? So what I want to ask you, and somebody gets a brownie point if they answer it first, which is the first bond to make between carbon what and carbon what? One and three, 1 and 3. Got a few of you in here. Right. So you could have either said 1 and 3 or 2 and 3. It would have given you the same molecule either way, because as I said, I give you symmetric stuff. So let's take carbons 1 and 3. So number 1 was the one with the methyl group on it. And carbon 3 was this one here at the top. I'm going to just take them and connect them. Okay. Check. Carbons 1 and 3 are currently connected. Now, there were hydrogens on here that I didn't show, right? So when that happens, this bond had to break and gets replaced with a single bond. So I will replace that. Check. And this bond here has to break, and that's what goes on to form the double bond between carbons 4 and 5, right? So remember that the carbon between the two dienes, those carbons are the ones that are going to form the new double bond, okay? So I'm going to just take this and flip it basically. I really think a model kit helps immensely with this. You guys can disagree with me, I don't know. All right. And that's going to cause this last carbon's double bond to break, right? It won't get to stay as a double bond forever. So I want you to think about what happens when carbons, which numbers did I have them? 5 and 6. When 4 and 5 form a double bond, will this be more of what we see on the test because the ones in the book was much, much more complex? I mean, it's kind of the same thing as the ones in the book, I thought. Okay, so now I'm missing one bond, right? So when I did my initial reaction between carbons 1 and carbon 3, it left this here as a carbocation, right? And so the second double bond that breaks, which would have been here to here, is now going to swing up and attack that. Okay. So then you can draw it, right? And actually I jacked up the stereochemistry because it should form the endo product, which would be within the ring. Okay. Now, there are different ways you can draw this. Oh no, I didn't jack it up. That's how I wanted it. Sorry. Usually the easiest way I think to draw it is where you have your double bond on one side or the other, okay? Because if you can keep that in mind, you can always see where the initial ring came from, okay? Just always kind of keep that point as an anchor. Why does my computer keep doing this? Does anybody know why a computer would just keep minimizing all my screens for no reason? Because if you do, I could use your help as a computer tech in my office. find that very weird. Okay. So anyway, that's what you would have. And then if you want to go about drawing these, you know, you can do them on KimSketch, but I think it's easiest, you know, seriously, to just like look at the model, tilt it a little bit, and then start drawing. So let's see. I got something that looks like that. I got something coming out at me. I got something that goes behind. Something that comes out over here. And you know, I don't judge you guys for crappy drawing on an exam if that's what it is. This one, whoops. This one, because we started off with a cyclohexane instead of a cyclopentane, would actually have 2 carbons at the bridgehead. And then we would have the carbon down here still and the oxygen down here. So I'm just drawing it the way that I'm looking at it, where this is kind of behind and then the OH is in the front. So that's essentially how I do Diels-Alder reactions. Actually, that's actually how I do basically any reaction that I'm having trouble visualizing. I mean, I think that it's easiest if you can number everything, and then if you need to make a model, you can do that. If you want to come in tomorrow having, I think, was that you, Kayla, that you already had a couple of double bonds already made so you can make things faster? That's absolutely fine. If you want to come in with a cyclohexane already made, just in case you need one, you know, for chair stuff, that's fine. I don't mind you guys doing that. I still need to check and see if the ACS exam allows us to use those on the final. Alexandra did? Okay. So, I mean, I think that what I just gave you was a fairly representative problem. But there are a lot of them in the book for you to practice with, so does that answer kind of helping with how to do a bicyclic with a Diels-Alder? Like, I really think it's a lot easier if you do them by numbering them. But that goes for anything that you have to kind of make into a ring, because otherwise it can be really hard to kind of see where things are coming and going. So here, thanks, Shelby. I will act like this is like a, I'm talking about conjugate thermo. So in the book was a cyclooctane. I mean, you could do a cyclooctane too, same way, but just make a model and then you can see it. Was the cyclooctane the diene, or was it the dienophile? Okay. So I'm just going to slightly rotate so you guys can see my beautiful molecule here. Conjugated bonds. So I could ask you questions about how to do addition reactions with conjugated double bonds at various temperatures. Hot being anything over basically 40 degrees and cold being anything like 0 or below. So something warm or something cold. I need you to know which one's the thermodynamic product and which one's the kinetic product. I need you to understand, I mean, I put it all on the study guide, that I need you to understand that especially conjugated double bonds absorb UV light. And I need you to know the Diels-Alder reaction. So there wasn't a whole lot from that chapter I'm holding you guys responsible for, because a lot of it was very kind of theoretical in nature with the instrumentation used. And I don't know, I felt like we didn't need that for what we need to know for this class. So I just kind of cut that out. Does that make sense? Yes. Yes, Kayla. That one is actually not that bad because it's basically like an elimination reaction. And then, so think of it as a standard elimination reaction, and then you do an addition reaction into it, essentially. So that's the nucleophilic substitution reaction. Which nucleophilic substitution reaction? Are you talking about the benzene one? Yeah, it's a nucleophilic aromatic substitution is what it's considered. So, that one, I just felt one of my bonds fall. Sorry. All right. So if you're talking about benzene chemistry, and remember, we have to heat the bloody heck out of this stuff. So you have some sort of group here that we will call leaving group. Oh, wait. And I think the only ones that we covered in your book, and I can double check this real quick, I think they were all in the vein of halogens for those leaving groups. Just double check real quick. Oh, that's the wrong chapter. Yeah, so your book shows, I don't know if I can hold this up for you to see. So your book shows a couple of examples, one's with chlorine and one's with bromine, both of which can basically undergo the same sort of E1, E2 type reaction that we've seen before, where you've basically heated it to the point where it's going to do it. Oh, thank you, Crystal. I see that you have that there now. So the hydroxide that you're going to use, or you can use NH2 minus, so instead of sodium hydroxide, you could use sodamide. And so the base, the strong base, is going to deprotonate the carbon alpha to the leaving group, the same way we've done it with other kinds of elimination reactions. That's going to cave the electrons in to form a triple bond and kick off the leaving group. Then in the second step of the reaction, you're basically going to be able to add in, using an acid catalyst, because you have HCl in the system, or in this case, HBr would be in your system down here. And so what you're able to do, because it's really going to want to reestablish that kind of really nice normal benzene structure because it's so stable, it's going to be able to add that water into that triple bond to make it work a lot better. Now that's kind of weird because every other time we've added a triple bond, you form the enol and then that shifts to the ketone, right? That's where that equilibrium goes. But in the case of this, it's the same exact chemistry, literally, okay? An elimination followed by an addition, the same exact way you would ever do it, ever. And then the difference is that this is kind of an enol. It just happens to have two other double bonds with it that makes it aromatic. And because of that, it's super stable, and so it's not going to break apart and form the keto form, okay? So I think that that one's pretty straightforward because it is very similar to the other reactions that we've done. It's just you have to do it at really, really freaky high temperatures. So remember that there are... Seriously, why does this keep happening? I really don't understand why my computer just automatically minimizes everything. So there is a, let's see, hydrogen here, and it doesn't matter which one you actually grab, okay? Either one of these is going to work. So let's just put in an OH with, let's see, if you haven't noticed, it'll always put in hydrogens to make everything saturated unless you specify that it has a charge on it or if you put extra things on it. So let me put in my arrow table, needs to come up. Hold on a second. Yes, Alexandra, because the benzene ring is even more stable than the stable ketone. There we go. All right. Okay. So if I put in, let's do my base attacking there. Okay. That bond's going to break, come in and form the triple bond, and that's going to make the leaving group leave, because that's what leaving groups do, right? So then that's going to give me my benzene. Okay, so let me put that together. Oh, come on. There we go. Why won't it let me just delete certain? Oh, because it's not on structure. Sorry. It wouldn't let me delete certain groups. All right. So I'm just going to delete that hydrogen for simplicity. It's not that it disappeared. It's still there. But the important one is that that's no longer there. So that's the benzene molecule. And that's, if you think about it, if you actually tried to make a model of that, you would feel an immense amount of strain in the molecule itself. It's not going to want to have, because if you look at that triple bond, that's sp hybridized, right? Sp hybridized things are supposed to be linear, and that's not going to be able to be very linear because of the ring. The only reason it can happen is because you're heating it and putting it under such immense pressure. So if I take this reaction and do this, okay, so that's basically step one, and I have HCl or HBr leaving, whatever it was that you had as your leaving group. Then the next step is essentially to add in OH minus, or let me actually just re-steal that OH minus. Oh, come on. Okay, so now that OH minus is in the reaction still, right? And that's going to be very nucleophilic. And in this case, this is going to attack right here, okay? So I can show, pull back up my drawing, show my curved arrows again. Nucleophile text electrophile. There we go. And then this bond here can come out and grab a proton, and we have plenty of protons in the solution, because if you have hydroxide, you're going to have things like water. If you have this reaction, you already have the HCl and the or the HBr in the system, so you have protons available, right? So, you know, I think that's the easiest way of showing it, and then you would just have the hydroxide. Now, the hydroxide, if you look at this, could attack equally at carbons 1 or 2, because the molecule's symmetric, and it would have an equal opportunity to attack either one. That means if you had a substituted ring, you could get multiple products. We didn't focus on that, but it's just something to be aware of, that you could get multiple products if you have something like that. So I hope that that answers your question. Who was that Kayla that asked that? Yeah, Kayla asked that. It's doing it again. You can tell every time that it messes up because I have to minimize the screen and maximize it again, and it messes up the feed. So sorry about that. No, I never, for mechanisms, I only ever give you one product and one starting material. And I give it to you so that you can work on it. Okay. It's really weird, your book doesn't even give mechanisms for a lot of that stuff. It like gives like half mechanisms. Jason, should we be able to write the hybridization of the molecules or the molecular orbital diagrams in that chapter of the book? Molecular orbital. Are you talking about where you, like how I showed on the board with the pi bonds sticking up? You should be able to draw those. I don't have you guys draw things like this, like the molecules, but that's because I have you guys work with the model kits already, so I don't find these as useful. But yeah, if you can draw, you should know where orbitals are and what type of hybridization things have. Yeah, generally speaking, you would put a positive sign if you have more than one product. Why are you having trouble with the nitrogen inside the ring? If it can meet all of the requirements for aromaticity, okay? So those requirements are, and I'm not going to type these because I think it would just be easier to say them. It has to be a ring. An aromatic ring has to be a ring. To be aromatic, it has to fit Huckel's rule, so 4n plus 2, right? So we covered how to do that. It has to have conjugated bonds that would exist in resonance inside the ring, going around the ring, just like benzene. And so sometimes if you have the heterocycles, so oxygen, nitrogen, sulfur, inside the ring, sometimes their lone pair electrons can contribute to the resonance through, or contribute to aromaticity through resonance, okay? So always remember that if something can be aromatic, it will. I've said that like 10 times, but I'm not joking. If something can be forced to be aromatic, it will be, all right? And that's simply because it's super, super stable that way. But it'll actually go through and rehybridize things that should look like they're sp3 hybridized. It'll rehybridize them to sp2 hybridized to keep it planar, to keep those electrons cycling around in a planar ring, okay? So if you have, let me pull this up. So if I have, whoop, what have I done? All right, I think my mouse pad on this computer's like having problems, might be what's going on here. Okay. So let's see. Is that molecule aromatic? Yes or no? No. So it's not aromatic because if you look here, there's 2 hydrogens there, right? There's 2 hydrogens there. There's no way that those electrons on the nitrogen can come in, and there's 2 hydrogens here also. Whoops. There's no way that these bonds can come in and form a double bond to have resonance in the ring because there's already a tetrahedral sp3 hybridized carbon there, okay? So not everything with a heteroatom and 6 electrons is going to be aromatic, okay? So it has to fit all those criteria. The resonance has to be able to go around the ring. It has to be planar, but it will be planar if it's you know, if it fits all the other criteria to become aromatic, it will be planar. So everything would be sp2 hybridized. And so then the thing you have to look for then are those cycling electrons. So if I have, like, let's see here, put a nitrogen there, let's just put a bunch of nitrogens in a ring. I have no idea what that ring's called. It probably begins with a P because all those rings with nitrogen begin with P. Triazine. Well, that makes sense. Okay, so let's take this molecule triazine. If you notice, there are conjugated bonds and or electrons, right, that can have resonance that goes around the ring, and that's what's going to stabilize it. because it has 6 electrons, that fits Huckel's rule, and so that's going to make it aromatic. Okay, it fits the criteria for aromaticity. If I had one of these double bonds gone, I couldn't do it because that would have 2 hydrogens on that carbon then, and you couldn't push a double bond there. I hope that makes sense. So the thing with the 5-membered rings with the heterocycles, and that's why those actually work, is because if I have something like that, there is no CH2 group anywhere on there. So these electrons on the nitrogen can go and form a double bond. That can move, right? And so you're going to be able to move that around the ring still. So that's why you can kind of do that with 5-membered rings, but you can't do it with 6-membered rings. If you have a CH2 group in there, it's not going to be able to contribute to the resonance. So hopefully that makes sense. All right, it's 9 o'clock and I have to read a 20-page paper for tomorrow morning, so a couple more. More than 1 hydrogen on a carbon in a ring. Oh, okay. Do I have to like pay Arby's if this is on the internet? Or maybe they pay me. Naming something. Okay. Where's Crystal's? Oh, Crystal hasn't asked it yet. Benzene rings. Oh, there you go. Ask away, Miss Molinius, as I take apart my model kit. Think of the endo products as being the axial ones, and think of the exo products as being equatorial to a ring. That's how you can tell the difference, and the endos are the ones that are favored. Yeah, I usually, that's a personal me thing, and a lot of other chemists do it too, but, you know, a lot of times we don't actually draw the lone pair electrons on our rings because we assume that they're there. So it's important to know if the ring has electrons, whether or not they're going to play a part or not. So if I was putting in, oh, wait a second. Need my full menu here. I haven't had to add electrons in a long time. Oh, for the love of goodness. Oh, and I don't know if you guys know that if you go under the templates window, there's actually a bicyclic feature there where you can a long time ago I looked up how to do electrons, but I don't remember how to do it, I'm sorry. But what I can tell you is that, oh, I'll just do it this way, it'll be easier. I can use periods. Oh, come on. Why does it keep doing that? Okay. That is totally taking the super special way of doing electron lone pairs. Alright, so if I put some here, and then I put some here. Oh, come on. Why do I keep doing that? I don't understand why when I copy and paste it, lone pair electrons. Odd. Anyway, so if I have lone pair electrons on all these nitrogens, they're not actually part of the resonance of the ring because the ring doesn't need them. It already has the double bonds there. So if you already have something in the ring that's going to be giving it those bonds, you know, or giving it, you know, the aromatic stuff, you don't need the lone pair electrons, and so you can think of those as being in the hybridized orbitals that are pointing outwards from the plane of the sp2 hybridized atoms. Now, if it's something that needs to be part of the ring to contribute to aromaticity, then yes, it's going to, you know, be up in that plane, cycling around in those pi bonds. So let me move this back over. On the left, the imidazole, yes, that is aromatic. Yes. I've been saying above the plane and in the plane. Both of those rings are aromatic, Crystal. I don't usually use the term perpendicular or orthogonal. I usually say above the plane or with the plane of the molecule, but it's basically the same thing. Yeah, maybe my left is different than your left on this, I don't know. But yeah, both of those molecules are aromatic, Crystal, because they fit all the criteria. When I'm saying above the plane, I mean they are, right, so the thing about aromatic molecules is they're planar, so they're flat, right? So if I have something flat, right, there are things that will come out of the plane, like this, and then there will be things that come up and down from the plane. The things that come up and down from the plane, in the case of an aromatic ring, are those unhybridized p orbitals that contain either the pi bonds, the double bonds, or the lone pair electrons if they're needed to fulfill Huckel's rule. Okay? All right, I hurt you guys and I love you, but I have to go read 20 pages for a meeting I have before your class starts. Also, I gave Miss Donna my exams because if the meeting goes over a few minutes, I want you guys to be able to start your exam on time. So, and not be like, hey, by the way, I cut 10 minutes off your exam, have fun. So, if I'm not there, naming. There was some naming at the beginning of the video as well, so look at that. But there's lots and lots of naming problems in the book. I do tend to favor the naming with the numbering. Just personally, that's what I usually do. Because it's like an easy system, but know the orthometapara system. It's real easy. Everything's still alphabetical and everything goes as a prefix on the ring. Remember that there are things like phenol, there are things like toluene, you know, have those memorized. I hate memorizing, but there's a few of them that I need you guys to know if you want to be considered educated chemists that have like passed an organic chemistry class. So, yeah, that's where we're going to leave that. So, I'll probably still be able to answer a couple email questions like, you know, tonight. I don't have to be on campus until 10 o'clock for that meeting, so I can go to bed a little bit later, you know, like 12 or 1 or something. So if you have questions, try and get them to me before midnight, because if you get them after midnight, I might not be able to answer them before class starts tomorrow. But it's been great. Thank you for coming and talking to me, and I will see you guys in the morning, okay? Study hard. Let me stop.